Okay, good morning, everybody, and thank you very much for joining me this morning for what's largely a repeat of our introduction to renewables presentation. It is one that you may have seen the majority of before, but there's a few new little bits in here, especially around the energy hierarchy. So we'll talk a little bit more in detail about that. Obviously, if you're watching this live and not on YouTube, then you will already know about Meshwork. But Meshwork is our social media platform for the built environment professionals and people who are interested in sustainable development. And we're closing in on 1,000 members now, which is brilliant news. We are looking to get to that 1,000 members by the end of the year. So we would ask that, if you know somebody who isn't a member of Meshwork and works in this space, please get them to join and give us a shout out on social media. And if you want to, you can always add the logos to email signatures and those kind of things. Because the more we can spread the word about this, the more the community grows, the more useful it becomes to everybody involved, which is fantastic. Meshwork is also developing, and we are shortly going to be running our first actual climate literacy course. So this is a course that will run over 3 consecutive Friday mornings, starting on the 26th of November. So let's talk a little bit more about today's webinar. So we'll start off with a little bit about Mesh Energy and who we are and what we do. And we'll also look at a case study of one of the projects we were involved in and how that project came about and why we chose the technologies that we did on that project. We'll talk about the energy hierarchy, and there's a little bit more in this presentation than there is usually in our Intro to Renewables presentation. And we're going to talk a little bit more about that energy hierarchy and why it's so important and where some of the where you can really reduce cost in a project by following the energy hierarchy. Then we'll talk a little bit about some of the heating technologies. So that's ground source heat pumps, air source heat pumps, and biomass. So those are the sort of primary heat sources that you might use on a sustainable building. And then we'll talk about some of the supporting technologies that go alongside those. So that's solar PV, battery storage, and mechanical ventilation and heat recovery, or MVHR. Then we'll look at the specification and design considerations for each of those technologies in turn. So those are the things that, if you're an architect, which I'm sure many of you are, those are the kind of things that you need to be considering when you're designing a building for some of these sustainable technologies. There's a little section at the end about government subsidies. Although government subsidies are, sort of dwindling a little bit, there are some government subsidies out there, and they're also worth looking at local subsidies as well, which obviously we can't cover in this. But for example, in the town I live in at the moment, the East Hampshire District Council are offering grants, straight up grants of up to 30% of the installation cost of a number of technologies, including things like improved insulation, but also solar PV, air source heat pumps, and other things. So so those local grants might be worth looking into as well. And finally, we'll look at some of the next steps and how you may work with Mesh Energy or with a similar consultancy to turn aspirations into realities and work on that. So let's start with the beginning. Who are Mesh Energy? Well, hopefully, because you're here, most of you already know this, but we're a small independent energy consultancy. We're based in Farnham in Surrey, and we're really set out to with a purpose, which is to inspire and forge a sustainable legacy. So the idea is we want to build buildings that are generally sustainable, and we want to help architects do that, and we want to help homeowners do that. By offering holistic advice about the whole building, and not just being somebody says, well, we'll put an air source heat pump or a ground source heat pump in. We want to look at the whole building and how we can make the whole building as sustainable as possible. Increasingly, that means also looking at embodied carbon as well. So looking at how the building is constructed and the carbon that goes into actually producing those building materials and how to reduce that. So let's talk a bit. We're going to talk a little bit more in detail about that thing that we mentioned before, which is called the energy hierarchy. And the energy hierarchy is sort of summarized in this little table. And really what it does is it looks at the building location, function and form as being the top level, because that's the thing that could have the biggest single impact on a building's energy performance. Then look within that building at the individual elements and their design and how to improve those. So that's insulation, it's the amount of windows, it's the amount of doors, etc. Then look at air tightness and ventilation, because air tightness, leaky buildings use a lot more energy than airtight ones. So it's the old adage of build tight, ventilate right. And only then do we get to the renewable technology, which is obviously where the focus of this presentation is. But I just wanted to sort of talk a bit more about these top elements, because actually they're really crucial. So starting at the top, building location, orientation and form. Now clearly, if you have a building which has a very large external surface area, it is likely to lose more heat than a similarly insulated building with a smaller external surface area. That's simple physics, will tell you that. But also things like orientation. So can you make use of a south-facing facade to collect heat in the winter? But obviously you don't want a building to overheat in the summer. So you can look at things like canopies over south-facing windows so that they do collect heat from the sun in the winter. But then that canopy shades the windows in the summer so that those same rooms don't overheat in the summer. That, of course, if you're looking at a retrofit project, may not be possible to influence at all. So I've put a line through it because it may well be you can't influence that, or you certainly can't influence the location too much. If you've got a plot of land, you can't really pick it up and move it. So you have to pretty much deal with what you've got. But on a new build, clearly you can rotate the building on a site to some extent in some circumstances, and obviously you've got an awful lot of influence over the form. So working down, fabric element design, this is the bit we'll concentrate on a little bit more in a moment. But really that's about insulation. It's about choosing suitable materials so that you get good view values. But it's also things like making sure that you're not overglazing a building too much. It's very tempting to, if especially you've got a nice view on a south-facing facade, to put loads of glass on there. But you've also got to consider how that glass is going to perform. Remember, even the very best glass, its U value is probably still 10 times as bad as a well-constructed wall. So, you're going to lose an awful lot of heat through glass, even the very best glass. And of course, during the summer, large windows particularly will tend to cause overheating. So you've got to balance all the requirements quite carefully, and it takes quite a lot of thought and thoughtful design to get that balance right. Air tightness and ventilation, I think we've already touched on, but really, when you're getting down to on new build down to air tightness values of better than 3 meters cubed per meter squared per hour at 50 pascals, you really need to be thinking about some of the technologies that we'll talk about later on, especially MVHR, to make the best of that very airtight building you've produced, and to ensure that you get the right level of ventilation in each of the rooms. Renewable technology clearly has a part to play. As much as we can sort as many of these elements above out as we want to, ultimately buildings in the UK will still require some kind of heating in the winter, especially on retrofit projects. It is possible, but very, very difficult to get most existing buildings down to sort of passive house standard. Obviously, with brand new build, it is easier to get nearer to that passive house standard, but it's certainly not an easy thing to do, and it takes some thought. So renewable technology has a part to play, and that can be solar PV panels. It can be ground air source heat pumps. It can be things like solar thermal as well. It could be wood burning stoves in some situations. So there's all kinds of other things that you can do. And then working down, appliances and lights really are quite a small proportion of most buildings' energy use. So whilst lighting particularly is a focus in a lot of commercial projects for reducing energy use, where lights are used all day, and office buildings especially, it's seen as an easy win. The actual proportion of energy that's used through lighting and appliances is relatively small. So it sits quite a long way down that energy hierarchy. And finally, there's how people use the buildings. And experience shows that as much as people want to change their lifestyles in order to be more energy efficient, the sad reality is, as humans, we're too lazy, and we don't after a little while. We just fall back into our old habits. So it's quite hard to change that use area at the bottom. So fundamentally, what it comes down to is, as architects and designers, we have to design buildings that are inherently energy efficient. So in summary, follow the energy hierarchy and make economically viable and visually acceptable fabric improvements before specifying renewable technology. So what does that mean in practice? Well, let's have a look at this, this retrofit project we have here. So a fairly typical house. So let's look at some of the areas we might look to improve. Well, first area, we've got an open chimney here. That may well be connected to an existing open fireplace at the bottom of the in the living room somewhere. Open fires are a real drain on building energy performance. So if you've got an open fire, you have to have a large permanently open air vent. I think it's 5,000 square millimeters off the top of my head. And that has to go into that room. And then a lot of heat is going to escape up that chimney. Now, to counter that, we know that a lot of people like having a real fire in their living room. And on a retrofit project, I wouldn't say, oh, I'll just go and rip out every single fire and do away with it. So how can we balance those two things of that human desire to have that warm, cozy fireplace in our living room against building an energy efficient building? Well, one very quick answer might be put a wood burning stove in, especially one which is room sealed, so that the air is brought in directly from the outside into the stove, through the stove and back out up through the chimney. That instantly reduces the ventilation losses from that open chimney. But it might be, if that's not a priority, then actually the chimney could be removed and capped. Obviously, it needs to be ventilated to ensure you don't get dampness issues. But that will reduce the energy consumption of the building quite considerably. Obviously, roof insulation, hot air rises, we know that. So depending on what you're using the roof space for, you might well go for a cold roof, or we might go for a warm roof. Obviously, a cold roof may well be more efficient because you've just got this flat surface, smaller surface area which you're trying to insulate, and you can build that insulation up quite thick quite easily. But roof insulation, absolutely key. Obviously, wall insulation as well, especially in older buildings. If you've got a cavity, if there's a wall cavity, make sure it's correctly filled and filled by somebody who knows what they're doing, so you don't end up with moisture issues. But it might be that if you've got solid walls, then maybe external solid wall insulation might be a good solution. But improving wall insulation, clearly the walls are probably going to be the single biggest element on a house in terms of total area. So reducing heat loss through those walls could be quite crucial. Floor insulation upgrades. Obviously, heat does tend to rise, so losses through the floors aren't quite as bad as losses through ceilings. But an old suspended timber floor will lose quite a lot of heat. And if you're looking to put an air source or ground source heat pump in there as part of a renovation project, then it might be worth looking at how you can upgrade the floor insulation simply to reduce downward heat losses from any underfloor heating you're putting in, because as we know, air source and ground source heat pumps are most efficient when paired with very low temperature emitters such as underfloor heating. Glazing U values can be improved, double glazed windows. Obviously this building is pictured with totally forgotten the name of them, sash windows. That's the word I was looking for. With sash windows, you know, old sash windows tend to be pretty leaky, so you can reduce the draft around sash windows, around windows in general. You know, good well-fitting windows can reduce heat losses a huge amount. But you know, going for double glazed, you know, or triple glazed units can really help improve the U values. You know, if you replace an old single glazed unit with a modern double glazed argon filled or vacuum filled unit, you might be able to reduce the U value of that window by a factor of nearly 5. So you know, that's a huge saving, and it will reflect in the comfort of the home as well, not just in the fuel costs. And then obviously doors, you know, same thing about reducing drafts. You'd be amazed how many people get in contact with us, and we go and do an initial site survey, and you close the front door behind you and you realize you can still see daylight through the front door when it's closed, either around the edges or through the actual door itself. You know, anything you can do to improve that, so much the better. And it might be that you know, the actual original door needs to stay there, and maybe you need to think about, well, can I create a secondary sort of airlock within the building? You know, if you want the appearance of the original oak, beautiful front door that's been there for centuries, you know, can you do something internally that reduces that? And it might be something, you know, you might be able to do quite a lot just by putting a curtain inside. You know, a big heavy curtain could actually make quite a difference, quite a noticeable difference. Okay, so this is another little graphic here. It kind of explains the energy hierarchy, but in a slightly different way. But it's the same thing. It's talking about the same thing. So it's all about getting the reducing the loads on the building first, then starting to apply technology only sort of after you've done what you can to the building. So this is a little case study about a project we did in Privet in Hampshire. It's a lovely little village just off the A272 outside sort of Petersfield kind of area, if you know that neck of the woods. And this was a new build property. This is, I think, the east facing facade from memory, but I may well be wrong. And you've got this very large window. What you can't really see on here is there's a courtyard that sort of sits in the middle of the building as well. But Mesh were employed to look at this building. It's got a swimming pool as well as the main house. You've got this tower here, which formed part of our ventilation strategy on this building. But what we were asked to do is we were asked to look at alternatives to the oil boiler that they were going to originally install. So the solution we came up with involved a combination of technologies, and that was a ground source heat pump to produce space heating for the main house. And we chose a ground source heat pump because it would give the best coefficient of performance throughout the year, and especially during the middle of winter, when we thought the majority of the heating would be needed. Just excuse me for a second while so that was why we chose a ground source heat pump for the main space heating and domestic hot water. We then chose an air source heat pump for heating the swimming pool. It's an outdoor swimming pool, so it's going to be used in the summer. And during the summer, an air source heat pump will offer a better or a similar COP or even better than a ground source heat pump, and obviously has a much lower cost of installation. So from that point of view, that worked. And then bearing in mind that both those technologies above are electrically powered, it seems sensible to put a very large solar PV array in to provide power for those with and also power for the rest of the house. So that covers off an awful lot of the day-to-day loads when the occupants are there. So this was done in the days of the feed-in tariff of solar PV and in the days where the RHI was very generous. So in total, we reckoned that the running cost savings over the oil system would be about £3,000 a year, and with a total subsidy of £80,000, and that gave an overall payback of around 8 years against putting the cheaper capital cost of the oil boiler. That was the alternative. We also managed to develop a 45% reduction in fuel bills, which was quite impressive. So this is the plant room. So you can see in the foreground here, this is a Valence ground source heat pump. You've got the buffer tank here, and then this is another view from the brine side pipes coming in here, heating pipes going out there. This is obviously still in there's the flexible connections there, which are quite important. Down here we've got the ground-mounted solar PV array, which was mounted up next to the greenhouse, and this is the little air source heat pump, which looks like it needs a little bit of a wipe over, but that does the heating for the swimming pool. So how do these technologies actually work? Well, if we look at a ground source heat pump with ground loops, which is the sort of most typically used system, they would be around about 25% cheaper than an oil boiler to run, and they take about 3/4 of their heat from the ground through these ground loops, and then the internal unit, the ground source heat pump itself, turns that low-grade energy from the ground into high-grade energy you can use around the house using a refrigeration cycle. So anybody who thinks that a ground source heat pump or an air source heat pump is new technology, I hate to tell you, it's not. Everybody has a heat pump already in their house. It's in your kitchen and it's your fridge and your freezer. They're both heat pumps. There's nothing new here. It's just the application which is different. So this is proven technology. As I say, typically you'll be looking at between 3.5 and 5 as a COP, or that's the equivalent of 350 and 500% efficiency. So for every kilowatt hour of electricity you put into the heat pump, you'll be getting between 3.5 kilowatt hours and 5 kilowatt hours of heat out of the heat pump. Now, if you compare that to a gas boiler for every kilowatt hour of gas that you put into the gas boiler, you'll typically get about 85 to 90% of the heat out. So you'll get a COP of equivalent of between 0.85 and 0.9, or 90 to 85 to 90% efficiency. So costs, cheapest ground source heat pump installation is going to be around about sort of the £12,000 mark. They are more expensive than gas boilers and they're more expensive than air source, but they are significantly cheaper to run than oil. And that's based on oil prices as they were a few months ago. They are eligible for some subsidies still through the domestic RHI. Obviously, when the RHI disappears, there's the new £5,000 government grant, which I believe will be which ground source heat pumps will be eligible for. And in terms of planning, very little in the way of planning constraints, because basically everything goes internally. So the only thing you really need to think about with planning is just the groundworks that go alongside putting in the ground loops. And obviously if you've got a mature garden, which has been lovingly tended for years, you might not want to go through the rigmarole of digging that up to put ground loops in. An air source heat pump works much in the same way as a ground source heat pump. The difference is simply where it gets its heat from. And an air source heat pump, as the name suggests, uses the ambient air as its heat source. So even air at -25 degrees outside your house has useful energy in it, which an air source heat pump can extract. So if you type in air source heat pump into Facebook, you will find lots of armchair engineers who will tell you that air source heat pumps don't work when it's cold. That's not right. You'll probably also find people saying that they're noisy. That's also not right. Although you do need to consider noise when you're installing an air source heat pump, because a badly installed air source heat pump may be noisy, but the air source heat pump itself isn't noisy. It's poor installation which makes it noisy. The other thing you need to the other sort of big myth about them is they're very expensive to run. Clearly, if you take out a gas-fired boiler and you put in an air source heat pump, your electricity bill will go up. That is because you are replacing something which is producing energy from gas and replacing it with something that's just getting it from electricity. So it's not surprising your electricity bill is going to go up. However, obviously your gas bill will go down, and what you should find is that on average you'll get about a 10% saving over a gas boiler. Now, at this stage, if you've got a perfectly functioning gas boiler and you're not doing renovations to your house, it is probably not worth ripping out your gas boiler and putting an air source heat pump in, because the costs of all the changeover probably don't make that a good way of spending your money. Going back to the energy hierarchy, you'd be much better off spending that money on improving the insulation of your house. And we get several inquiries every week from people saying, I want to rip out my gas boiler and put in an air source heat pump. Can you tell us how to do it? And can you do a study on it? And our usual response to that is, don't do it. It's probably not worth it. Spend the money on insulation. But having said all that, if you've got a new build or your gas boiler has died, then it might be a good, or if you've got an oil boiler or an LPG boiler, then it is probably worth thinking about whether an air source heat pump is the right solution. So how do they work? Well, they run on electricity, as we said. They've used the energy from the air, and they produce both heating water and domestic hot water. Again, myth number 3, air source heat pumps do produce domestic hot water. Anybody who tells you they don't is incorrect. Typically, efficiencies are a little bit lower than for ground source, but you're still going to be looking at an efficiency of around 250 to 400%. That's a COP of 2.5 to 4, so coefficient of performance between 2.5 and 4. So for every kilowatt hour of electricity you put into your heat pump, you'll get between 2.5 and 4 kilowatt hours of heat out of your heat pump. And that's why they're cheaper than a boiler to run, because electricity, although it's more expensive per kilowatt hour than gas, these high efficiencies mean that you tend to get lower energy costs. In terms of cost of installation, an air source heat pump itself will cost you around £6,000 upwards to install. Obviously, the bigger the unit, the more it's going to cost. There's very little in the way of groundworks. What you will need is somewhere for the external unit to sit, and you can see in this photo here, you've got these this soakaway built underneath this gravel here, and that's because behind this fan here, you've got the evaporator. So this whole box here, this part of the box, has what looks like a big radiator behind it, and that has liquid refrigerant coming into it, and at the bottom, and then that turns into gas, which goes out to the top, and that's where the heat is collected. So this down here, this is going to be about -30 degrees C, and by the time it reaches here, it might be at -15 or so. and you're extracting heat. Obviously, if you chill air by that amount, then you're going to get some condensation, and you get condensation on the evaporator. And about every, depending on the humidity on the day, about every 20 minutes or so, the heat pump will have to go through a defrost cycle. And what will happen then is it will reverse itself, pump a little bit of heat into the evaporator, and that then causes all that condensation to drip off the evaporator, and that's then collected, and usually that's then just piped straight into a little soakaway underneath the heat pump, or it can be piped straight into a rainwater drain. In terms of planning permission, in most cases, air source heat pumps can be done under permitted development. However, if you've got in a conservation area, if you've got certain types of listed building, if you're going to put the unit within 1 metre of a boundary, if you've already got another heat pump on the site, if you've already got a wind turbine on site, then you may need to get planning permission. So there's a few different caveats to that, but that's always worth checking with somebody like Mesh. Biomass boilers are probably something that we don't install or recommend very often, but they can be a good idea in some situations. They are particularly good if you've got a very large property which has plenty of external space for all the equipment and is very difficult to upgrade thermally, meaning that you do require the higher flow temperatures that a boiler will give you. They can run on pellets, chips or logs, and they're used for basically heating up the hot water. They'll give you the high flow temperatures that a heat pump will struggle to get, or if it will get there, then it will do it at a relatively high cost. As I say, often used for larger buildings. In terms of costs, you're really talking about £15,000 plus. They are cheaper to run than an oil boiler. It's they particularly are used quite a lot on historic properties. Although even people like the National Trust tend to be moving away from wood biomass now, and they're tending to go more towards heat pumps and trying to upgrade properties that way. There is still a subsidy eligibility for biomass through the RHI, so it may be worth considering in some situations, but they're not something we typically recommend. So moving on to the supporting technologies, we'll talk first of all about solar PV, which is probably the easiest retrofit of any of these technologies, and most properties you could put some sort of solar PV array on. Whether it's economically beneficial to do it in every situation is slightly different, but you can in many situations. So what does PV do? Well, PV stands for photovoltaics, which sort of leads you down that sort of thought of electricity. But basically what it does is they're a big panel. When sunlight lands on the panel, it excites electrons, and you get a potential difference which you can then use to create electricity, which you can use to run things. What comes off the solar panels is DC. As you may know, our plugs in our houses are all AC. So between the solar panel and your plugs, you have to have a little box called an inverter, and that turns the DC electricity produced by the solar panels into the AC electricity that you can use. It comes in lots of different forms, but by far the most common are these panels that are about 1.7 by 1 meter. There's a rough guide. They're about 45 millimeters thick typically, and they can either sit on the roof. They can be ground mounted like they are in this example. You can also get solar tiles as well. They tend to be more expensive and have lower efficiencies, but they maybe give a better aesthetic. And typically they cost between about £3,000 and £7,000 for a sort of typical installation. Because they give such good paybacks, they're not actually no longer eligible for the main government subsidies, although there are still some local subsidies in some areas which you can put towards solar PV. And if you produce any electricity you don't use on site, then that can be sold back to the grid. And there is a requirement for electricity companies to buy that electricity from you through something called the Smart Export Guarantee. So the Smart Export Guarantee guarantees that you will be paid something for any solar energy you produce. Rates at the moment, so I haven't checked actually within the last few weeks, the last time I checked, rates were between about 0.5 pence per kilowatt hour at the lowest end, up to about 5.5 pence at the highest end, depending on which provider you were with. Obviously, changing electricity providers at the moment is tricky, so it might not be something to bank on just at this precise moment. But the Smart Export Guarantee is there, so you will be able to get some sort of payment for any excess electricity. What sits quite nicely alongside solar PV is battery storage. So battery storage allows you to save any energy that you produce for use at a later time. And it also allows you, if you've got a variable electricity tariff, to charge the battery from the mains at periods when electricity is cheap, and then use that electricity at periods where the electricity is more expensive to save you a bit of money. There's loads of products, loads of installation options available. Some of them offer backup in the event of a power cut, some don't. So don't think just because you've got a battery you're necessarily going to be covered for a power cut. That is not necessarily the case. But you're talking about typically a cost at the very lowest end of about £3,000 for a battery. The Tesla Powerwall shown here, typically installed, you're probably looking at about 7.5. We reckon per kilowatt hour of storage about £500 is the sort of going rate. The Tesla Powerwall is about a 13.5 kilowatt hour battery, so it gives you an idea. But yeah, we're expecting prices of batteries to drop 15% a year. Is probably a bit on the generous side, bearing in mind what inflation is doing. But that's the kind of rough direction of travel we can see. And currently, there are no subsidies for batteries. In terms of the economic case for batteries at the moment, it's pretty marginal because a battery has a finite life and it obviously has a finite capacity. What you find is when you do the maths that it works out roughly cost neutral to have a battery at the moment. But obviously, as electricity prices fluctuate, it is likely to become more economically beneficial. Okay, the next one is more on the mechanical side again. So we're looking at mechanical ventilation and heat recovery. So this is all about getting fresh air into the building in the most efficient way and recovering heat from air that is leaving the building. So how does it work? Well, at the center of the whole system is this unit in the middle, an MVHR unit, which is a big box. This will tend to sit up in the loft, or quite often it will sit in a utility room. But that box has two fans, a heat exchanger, and some filters in it. What that does is it extracts warm, stale air from the wet rooms around the house. So that will be the kitchen down here. If you've got a utility room, you'd be utility room as well. WCs and bathrooms. It takes that warm, stale air through the box, and that passes through a heat exchanger. As it goes through the heat exchanger, it loses heat, and that now cool stale air is ejected out into the environment. On the other side, cold, fresh air from outside is taken into the unit, is passed through a filter and passed through that the other side of the heat exchanger. And that then pre-warms the air, which is then supplied to all the habitable rooms around the building. So that would be your living room, any bedrooms, and things like if you've got a snug or dining rooms and those kind of rooms, then you'll supply air into those spaces. Now, what that does is it means that rather than chucking away warm air that you've spent money heating up, you're just recovering that heat, but you're still getting fantastic filtered air throughout the entire property. And the feeling of freshness that you get from a well ventilated house with MVHR is really quite something. What you find is that the bits that typically architects tend to miss out on is they forget to leave enough space for this ductwork, and it can make the ductwork installation quite tricky to design. So please, architects, leave plenty of space for ductwork, and remember that ducts don't go through things very well. So when you're designing structure, when your structure is being designed, think about leaving a void where you can run those ducts uninterrupted. So that's physically what one of the units looks like. It's a Ventaxia unit. So you've got the little control panel on the front, although you probably can't see it there. Just turn the pen back on. Those two little pull-out things here and here are the filters. And then you've got the air, so you'll have the four different connections to the ductwork of those points there. Typically, MVHR units can recover between 75 and 95% of the heat from the air. So they're really good. And of course, if you've got a very airtight building, then they allow you to operate these very super airtight buildings without having to cut holes for vents in the facade. So it works really well. As a rule of thumb, obviously these have an electric fan in them, so they do have a running cost associated with them. The rule of thumb is if the building's air tightness is worse than 5, so 5 or greater, then the running cost of the MVHR unit will not outweigh the saving that you'll get on the heating bill. Between 3 and 5, it will be about cost neutral. If your air tightness is better than 3, MVHR is absolutely essential and will definitely give you a significant running cost saving. So those are the sort of rules of thumb. We would be encouraging architects to think about, especially on new builds, trying to design air tightness down to sort of 1. So you're really getting super airtight buildings. Overall, because they tend to be fitted in quite well insulated, quite airtight buildings, you can see about a 30% loss, 30% reduction in heat losses. And as long as it's designed correctly, the running costs are very low, and they're very quiet. I was in a house with MVHR on Friday, and even standing directly under the vents, you could not hear it at all. It was super quiet. So the next things we're going to talk about are some of the sort of spec and design features that you need to think about. So let's talk first of all about electrical supplies. So a lot of the technologies we've talked about are supplied by electricity. Electricity has the potential to be fully renewable. Obviously, at this stage in the UK, the renewable proportion of electricity is going up all the time, but we're still generating a significant amount of our electricity from gas. But it is getting greener and greener. And obviously, coal power stations are now largely offline. We've got Drax, which is producing energy from biomass. We've got a few other, obviously got a fair amount of nuclear. We've got a lot of onshore and offshore wind. So our electricity grid is becoming greener. But with that, obviously, with the electrification of heating, we can start thinking much more often about 3-phase power supplies for domestic buildings. As a rule of thumb, if your building is less than 300 square meters and reasonably well insulated, you will probably get away with a single phase power supply. And that's the standard power supply that most buildings will already have. So 100 amp single phase power supply or 23 kVA power supply is pretty much the standard. If you've got a building that's over 300 square meters, it is likely you will need a 3-phase power supply to make an electrified heat pump heating system work. And that's especially true if you're also cooking with electricity. You've also maybe got an EV car charging point. If you've got a swimming pool, any of these other things that are likely to use a fair chunk of electricity, then anything over 300 square meters, you really need to be thinking about 3-phase. 3-phase upgrades can cost anything from £1,000 upwards, really. So it's worth thinking about this early. If you've got a particularly isolated rural property, I have seen some really quite extortionate quotes for 3-phase power supplies. I think the highest one I saw was nearly £150,000 for a 3-phase upgrade. For biomass boilers and solar thermal systems, single phase is normally all that's required. If you had an absolutely enormous commercial biomass boiler, you might need a 3-phase supply, but for anything you're going to look at domestically, single phase will be plenty. Solar PV systems, you're allowed to export to the grid up to 16 amps per phase, so that's 3.68 kilowatts for a single phase supply, or about 11 kilowatts for a 3-phase supply, without having any permission from the DNO, which is the distribution network operator. If you're going over 16 amps, then you need to get permission. In most cases, that's obtainable fairly easily. If we look at a sort of typical ground source heat pump installation, this just give you an idea of the sort of space requirements. This, I would say, is a pretty compact installation. I mean, you could probably squeeze it a little bit more than this, but this is about as small as you're going to get. This has got the ground source heat pump, a domestic hot water cylinder, and a little buffer tank in the middle there. So you can see, this is sort of 3 or 4 square meters, I guess, that you've got here, and obviously a big full height wall space behind. And the other thing to consider is just the height of domestic hot water cylinders. They can be quite tall. So if you've got particularly restricted roof ceiling heights, then that's something to consider. And obviously the takeoff for the domestic hot water tends to be on the top, so you have to allow a little bit of space above the height of the cylinder for that takeoff. Externally, depending on the type of collector system you use, you may need a fair amount of land outside. If you haven't got that land, doesn't mean you necessarily can't use a ground source heat pump, but you might need to look at boreholes rather than flat loops, and that's a bit more of an expensive sort of thing. If you're going for flat loops, the recommendation is an absolute minimum of twice the floor area, the gross internal floor area of the building you're trying to serve, and that's if it's a pretty well insulated high spec building, and if it's pretty favourable ground conditions. Probably more realistic is 3 to 4 in most cases. If you're doing flat loops, you can't put them under impervious paved areas or where there's trees above, because the flat loops rely on rainfall to bring some of the heat back into the ground, and trees could obviously damage the pipework with their roots. So as I say, equipment, park space, we've kind of covered that already. Air source heat pumps, we've already seen this this picture of the Valent units, but typically externally you're looking at about 2 meters by 2 meters. That's not because the units are particularly huge, but because they do need good ventilation around them. So there's quite a significant area that they need to have in front of the fan to allow for the cold air to be taken away. And you've also got obviously got to get air into the other side of this unit. So this can come from various places. So yes, so there's three sort of flavors of air source heat pumps. This is a monoblock unit. You can see here. All the differences is that the monoblock unit, both the evaporator and the condenser side of the heat pump are in one box. With a split system, the evaporator side is in the external unit and the condenser side is in an internal unit. And typically then the internal unit is about the size of a conventional gas boiler. So you just said to sort of allow that space. Monoblocks are by far the most popular type of installation because obviously it reduces the amount of plant space required internally. A tower split system is basically a normal split unit, but has the hot water cylinder integrated into the condenser side. Okay, so solar PV, things to think about with solar PV, and this also kind of applies to solar thermal as well, but obviously the panels can go either ground mounted or roof mounted. Typically roof mounted is more popular. If you have ground mounted panels, they have to get planning permission. Obviously you want to avoid areas where there's shading, especially from buildings, because that's going to reduce the efficiency of the system. The absolute ideal is you have them directly, say, south facing on a 30 to 40 degree angle. But you can do an east-west split or just an east or west system. And that will lose you about 11% over a south-facing system with the same number of panels. So that's where you are there. With MVHR, I'm just going to put in the 10 sort of top things to think about. So the first thing to do is design it in early if you can. It's much harder to squeeze an MVHR system into a building that's not designed for it. Consider the structure when designing the ducts. Allow space around the unit for filter changes and servicing. So usually you have to allow the same depth as the unit in front of the unit because the filters go the full depth of the unit. Allow access within the ductwork system itself for balancing and commissioning. Think about silencers and manifolds, so they'll need some space, and that will help reduce any noise. Keep the MVHR system within the thermal envelope of the building. You don't ideally want to put an MVHR system in a cold roof because you'll lose some of the efficiency of the system, and you'll have to start putting a lot of insulation around the ductwork. Allow condensate drainage from the main unit. So because you're taking warm, damp air out of a bathroom, for example, then you're passing it through a heat exchanger, which is colder to recover that heat. You will get some condensate, and that obviously has to be drained away somewhere. Maintain the separation between the inlet and outlet ducts, ideally a couple of meters. You can reduce that a little bit, but that's just to prevent the stale air being recirculated back in with the fresh air. And to position the inlet ducts away from pollutions and strong winds. So we had a project quite recently where the house that we were dealing with was had an industrial building next to it, which had where they did a lot of paint spraying. And so what we did is we put the MVHR units on the other side of the building from where the paint spraying was taking place, and that had meant that we could then take fresh air in from as far away as possible from the paint booth, so you didn't get the smell of paint in the house at any point. So that's quite a sort of interesting one. And obviously allow space for the inlet and outlet ducts insulation as well, because again, those would be below the temperature of the house. So they need to be insulated so you don't get condensation forming on the outside of those ducts. And last but not least, government subsidies. The ever-changing feast of government subsidies. Currently, there's the domestic RHI, and this ends, this is paid over 7 years, and it ends on the 31st of March 2022. It's a totally tax-free subsidy, that end date is not the date for the payments ending. The payments will carry on for the 7 years, but that's the date for new applications. And to make an application, the whole system needs to be completed, installed, and commissioned. There are maximum payments for each of the technologies. So these are the payments per kilowatt hour of renewable heat produced. So you can see that ground source heat pump is more generous than air source heat pump. And what you'll also see is that when you compare ground source heat pump with an air source heat pump, is that the maximum payments are also higher. That means that historically ground source heat pumps have tended to suit larger properties, and air source heat pumps have tended to suit smaller properties because of those maximum payments. Biomass maximum payments are a little bit lower than ground source. And solar thermal, although it has the most generous payment per kilowatt hour of heat produced, also has the lowest ceiling payment. And those payments have been set to try and reflect the cost of installation. So because a ground source heat pump is more expensive to install than an air source, it gets a more generous kilowatt hour by kilowatt hour payment, but also more generous ceiling as well. Okay, so this is how Mesh works with our clients. So we can be involved all the way through the whole process, from feasibility and sort of early stage design, all the way through sort of detailed design and specification at stage 4, and then oversight throughout the installation. And most importantly, of course, is doing that post-occupancy evaluation as well, so that the next projects are informed by the previous projects. And it's quite important that we sort of complete that circle more and more, especially as things are changing within the building services industry. You know, it's important we learn from previous projects. Okay, I will now pick up questions. I'm sorry I'm a little bit over time, but you know, feel free to stay on if you want to, and I will pick up. There's about 14 questions by the looks of it in the chat, so let's have a quick look and see what those are. Okay. So Natasha saying we're seeing 11 kilowatt heat pump installations costing 15 to 20k in Oxfordshire. That sounds pretty expensive. Does that include the heat emitters? That would be quite interesting to know. Certainly an 11 kilowatt heat pump itself is nothing like that kind of cost. So it might well be that's including for lots of upgrades in pipe work, heat emitters, etc. Well, I don't know if biomass will be covered by RHI, to be honest. So from March 2022, obviously RHI is going. The new system that's coming out, this one-off £5,000 grant, the details that I've seen have been quite sketchy, and I wouldn't like to tell you whether it included biomass or not, because I would be guessing. I haven't read the detail. I haven't seen enough detail to be able to tell you that. Typical MVHR supply and installation costs, question from John. It very much depends upon the size and complexity of the system. I'm afraid that's a bit of a piece of how long is a piece of string type question. So probably the best way of answering that is, if you've got a particular property in mind, is we can do a feasibility study on it, and it will drop out from the feasibility study what the likely costs are for the supply and installation of MVHR. But our experience is that it makes sense if you have a building which has an air tightness of 3.5 or better, and between or sort of 3 and 5, it's going to be a marginal it's going to be a bit marginal. And if the building's less airtight than 5, then you really probably need to be thinking about improving the airtightness of the building before considering MVHR. So there's a couple of so Natasha's asked about, can MVHR also supply summer cooling? So MVHR, there is a system that Zender offer where you can put a small cooling unit into the supply ducts for the MVHR. However, I would caution about thinking of it as being a sort of air conditioning type system, because the amount of air that MVHR supplies is much smaller than an air conditioning system will move. So it will provide a proportion of cooling, it will provide a little bit of comfort cooling. It'll take the edge off the temperatures, but it's not the same as an air conditioning system. If your building needs significant amounts of cooling, then you really need to think about an air conditioning system or a reversible heat pump system connected to fan coil units, which gives much the same system. So that question's kind of been answered by Daryl as well. Yeah, he said exactly the same as I did, which is quite good. So thank you for answering that, Daryl. Sard, how good is air source heat pumps for cooling? Can we run 2 different circuits from the buffer vessel to heat the property via underfloor heating and cooling via FCUs? Yes, you can, and we've done that on a number of projects. So the question then is, do you want to have simultaneous heating and cooling? In most cases, you won't want to, but if you've got a particularly awkward property where, for example, you had one room that was very prone to overheating, even in sort of March time, it was a particularly bad room for solar gain, for example, then you might want to do simultaneous heating and cooling. If you want that, then you have to have 2 buffer vessels, and then the heat pump will be allowed to flip between heating and cooling. It will effectively charge the heating buffer, then it will charge the cooling buffer, etc. It's a pretty awkward system to get installed and working correctly. But for most cases, yes, you can do exactly what you suggested. Have your underfloor heating doing heating, and then have fan coil units to do the cooling. Is there any practical alternative to using a gas boiler for intermittent high water heating loads, e.g. showers in a football pavilion used intensively just on a Saturday morning? So, Jane, that's a good question. The answer to that is there's a couple of ways you could do it, but what you'd need to do is you'd need to store the hot water. You'd need to store a very large volume of hot water, and then so that you effectively stored enough hot water to cover that peak load. You would then probably have that system on a timer so that it wasn't so you weren't getting standing losses during the week when it wasn't being used. So you just have it coming on, very early on Saturday morning, so that by the time the football match is finished, the hot water was hot. And then obviously if you had a second set of matches in the afternoon, then you'd obviously have to size the heat pump or whatever to give you that heat. The other thing you could do, of course, would be to use, and this would be very electricity intensive, would be to use point of use showers. So you have the heating at the point of use. It would give you a very low install cost, and obviously it'd be very space efficient, but you would have to have a pretty sizable electricity supply to power that kind of thing. Daniel's comment made a comment about using fan-assisted radiators such as Dimplex Smart Rads for cooling. Just be careful, because I'm not sure whether the Smart Rads, no, the original Smart Rads weren't cooling compatible because they didn't have condensate drains in them. They were heating only, but I think they do now do a heating and cooling version. So just be careful with that one. Hugh, what's the cost and feasibility of borehole ground hot source heat pumps? So boreholes are more expensive to install than horizontal ground loops. In terms of feasibility, it's we would usually recommend boreholes on systems where there's cooling, because they are more efficient with dealing with cooling, and they store the waste heat from the summer, and you can sort of recycle that heat a little bit in the winter. The other big thing that changes borehole installation costs is the ground conditions. So what we do is, as a standard, when we're doing a feasibility study, we get a preliminary ground geotechnical report done by a third party, and get a sort of preliminary borehole sizing done, so we can get an estimate of the ground source of the borehole costs. Typically boreholes are about £20 a metre to bore. Obviously you've got smaller installations, you've got that cost goes up a little bit, because you've got the cost of getting the borehole drilling rig to site and all the sort of mobilisation costs. So often it tends to be more economically viable for larger installations. And again, that's another reason why air source quite often comes up better on smaller installations. So Natasha's asked about air source heat pumps that only do the hot water. So there are heat pumps which use exhaust air to prepare hot water, and those can be quite effective. What they tend to do is, obviously they are taking heat from the building. Now, if that's as part of a sort of MVHR type system, then that can be quite effective. But obviously what you don't want to be doing is just putting heat in one part of the building and then extracting it out in another part of the building for no purpose. So you just have to be a little bit careful of them. In most situations, if we're doing a heating, if we're doing a new build property, we wouldn't put a hot water only heat pump in. We would put in an air source heat pump which does both the space heating and domestic hot water. So you're getting your heat from outside. If you are doing cooling, there are heat pumps which can recover waste heat from the cooling side and use that to heat domestic hot water or a swimming pool. So eco-forests, air source and ground source heat pumps have that built in as standard on their reversible models. Glyn has asked, are there air source heat pumps which work in a similar way to a combi boiler to be able to give you on-demand hot water if your hot water cylinder ran out? No, there aren't. And the reason for that is that a combi boiler will generally have a very, very high power output. So 35, 40 kilowatts, that kind of region. The physical size of an air source heat pump that can do that kind of output is pretty big. And you're typically only going to be putting that type of boiler into a relatively small building. So it just doesn't financially make any sort of sense to do that. What you do tend to do is you do tend to put a larger hot water cylinder in with an air source heat pump than you would with a boiler, partly to offset that. And of course, you can also do things like run an immersion heater in the cylinder from a solar PV system. So you can use a product called a solar diverter, so that when you're generating electricity from your PV system, which isn't being used on site, you can you can dump that electricity through the immersion heater to heat your hot water up to a higher temperature, so that you know, obviously then you want thermostatic mixing valves on the taps and things, but that it allows you to effectively use that energy that otherwise would be exported to the grid, and that gives you a similar kind of return as having a heat pump that's got a COP of about 3. Glyn has asked, can you combine an air source heat pump with solar thermal to help boost your base temperature? Absolutely, you can. However, when you work out the economics of it, because solar thermal is a sort of one-trick pony, it's usually better to if you've got, you know, a finite roof space, to devote that roof space to solar PV and then use the solar diverter. That's usually a more economical way of doing it, because once solar thermal, obviously, once it's charged the hot water cylinder in the summer, then it can't do anything. So it's sat there doing nothing. Whereas, of course, a solar PV system can be producing electricity all the time, and you can be using it for lots of other things. So our experience when we've run the numbers is that in most cases, unless you have a particularly high hot water demand, is that the most efficient way to do it is to use that space for solar PV rather than solar thermal. And then obviously you can use that electricity to power your heat pump.